Hey everyone, welcome back, and today let's solve Leetcode problem 1261 titled Find Elements in a Contaminated Binary Tree. So we're given a binary tree with the following rules such that the root value, or the value of the root node in this binary tree input, is going to be equal to 0. And for any tree node or node in the tree, if the value of that node has a value x and the left node or left child node of that specific node or tree node dot left, as long as it's non-null, then we know that the left value of the current node is going to be 2 times the value x of the current node plus 1. However, if the tree node value has a value x and the tree node right value, basically the right subchild or subnode of the current node, if that's not equal to null, then the value of the right node of that current node would be 2 times x plus 2, where x is again the value of that current node. And these are how we compute the values of the left and right subnodes or child nodes. So now the binary tree is contaminated, which means that all of the values or node values in the tree have been changed to -1. And we need to implement this find elements class, as you see with this kind of class and methods here, right? So basically, find elements is going to be one of the methods, and it's going to take in a tree node and a root. Basically, it's the initialization or the initial init method. It just initializes the object of that class with a contaminated binary tree and simply recovers it. Whereas the find method, as we see here, with a Boolean return type, taking in an integer target parameter, it's going to return true if the target does exist in the recovered binary tree and false otherwise. And you'll see how that kind of plays out in the code as well. So in example 1, we have our input to be -1 and -1. Makes sense because we are told that all of the value nodes in the tree have been changed to -1, kind of that contaminated effect or property of the input node, as you may assume. And in this case, for input, we have 3 different methods. We have the find elements initializing class, then we have the find method called 2times, right? Again, what the find method does, it basically returns if that target passed in, or that integer node passed in as the parameter, if it actually is in that recovered binary tree or not. Right, in this case, we have null as our output, of course, because this is just the first call of the class, initializing the object of the tree. Then we have false, and we have true. False and true simply signify if these parameters as such, or these integer nodes, if they do actually exist in that recovered binary tree, right? And the way those kind of method calls would work, find elements.find with passing in 1 would return false. Why? Because 1 isn't a value in the tree, in the recovered tree, that is. However, find elements at 2, basically calling the find method with an integer target of 2 as a parameter, that would return true because, of course, 2 is a node value in the tree, right? We see it right here. It's a child or a right node of the node 0, which is again the root node, because we are told that the root node is always going to be equal to 0, and the right node would be 2 times that value plus 2, whereas the left would be 2 times that value plus 1. Right? So since this is 0, 2 times 0 is 0, and 0 plus 2 is 2. That's why the right node has a value of 2, whereas the root does have a value of 0. In example 2, we have our input binary tree to be a little bit larger, but obviously it still will be initialized to all -1s because that is what the problem tells us. And we can recover this to be 0, 1, 2, 3, 4, applying those computations of the left and right child nodes, starting from a root node of 0 and building our way down from there. And once we construct that binary tree, applying the input methods that were given, calling them, basically calling find 3 times with nodes 1, 3, and 5, we'd have true, true, and false. Because 1 and 3, the first 2 calls, indeed they are values or node values in the input binary tree after we recover it from the contaminated -1 tree. But 5 is not a node in that, so we return false for that call. And finally, in example 3, once we actually kind of construct or regenerate or recover this initially contaminated tree to these values, applying these 2 operations from left and right nodes for any node here, basically we get the node values 0, 2, 5, and 11. And in this case, calling the find method on 2, 3, 4, and 5. 2 is indeed in it, right? As you can see, 2 is a node in this recovered tree, but 3, 4, and 5, or rather 3 and 4 aren't, and 5 is, so it'd be true for 2 and 5, as you can see here, and false for 3 and 4, right? Because we're basically trying to find those integer node values in the recovered binary tree of our input. So for the constraints here, we're always going to be given that tree node at any value. It's always going to be equal to -1 because, of course, the input is always going to be contaminated, and the height of the binary tree is always guaranteed to be less than or equal to 20, basically meaning we have less than or equal to 20 levels in the binary tree. So we do have a limited number and finite number of nodes. And the total number of nodes is always going to be, getting to that portion, between 1 and 10 to the 4th power, and the total calls of the find function in that class find elements class is going to be between 1 and 10 to the 4th as well. And we're also finally given that the target integer, or the target node value integer, is always going to be between 0 and 10 to the 6th power. So that leads us to some important observations we can actually make to help us lead to our solution. And what is the first kind of main observation that really we can take away from the problem statement and from the examples? Well, that is that every node's value is always going to be uniquely determined by its parent's value, right? Based on if it's a left or right node, it's always going to be 2 times its parent node plus 1 or 2, based on if it's a left or right child node of the parent. Right? And we can build our tree using those properties or using those computations to actually generate or recover our tree and apply those find calls, right? And the values in that tree, they always follow that strict pattern. That's the main kind of observation or key takeaway that we should make. And they're always going to be based on these 2 formulas that were given here in the problem statement. That means we can always store them efficiently for a quick lookup time. And what does a quick lookup time remind you of? It reminds you of constant lookup times, which kind of remind you of hash maps and hash sets. More on that later. All right, so how do we actually store the nodes following that strict pattern with our strict formula? How do we find that in a quick lookup time to check when we're actually calling our find method to check if the current parameter or node is actually in the tree? Well, basically, instead of actually searching for that target value in the tree by traversing the whole tree in every single call of the find method, we can actually store it or store all the values of all the nodes that we actually build in the recovered binary tree in a hash set. And why do we use a hash set? Well, because it has a big O of 1 or a constant lookup time. That makes it a lot more efficient than a list or, a different data structure, right? So on a high level rundown, how is the solution going to work? Basically, we traverse the tree starting from the root node, and we assign the values based on left and right child nodes based on these given formulas or these given rules that we see in the problem statement, 2 times x plus 1 or 2 times x plus 2. And then we're actually going to store all the valid values of the recovered node values of the tree in a hash set, so that if we actually check for existence of parameter nodes in our find methods, we can do that in constant or big O of 1 time and implement that find function to actually check, well, is the value actually existing in our set? That's how we check if it's actually part of the tree in a very efficient runtime. And that actually leads us to our solution or to our code here, right? So first, of course, we have to actually initialize our object, calling or kind of coding up the init portion or the init method of this class. So I'm going to use the self keyword here in Python and initialize the self.values hash set. And this is going to be initialized to an empty set. Again, the key portion of the set is actually to store all the recovered node values of the recovered tree to check if any find call method does have a parameter that is indeed in our tree or not. Of course, in the recovered part, right? Basically, it's going to store all the recovered values, right? That's the main reason why we want this set, hash set, rather than a list for that big O of 1 lookup time. Because think about it. Since we're storing all the node values of our recovered binary tree that we build in this hash set, instead of actually traversing the main tree itself to actually check if a parameter of the find method, if that node is actually in the tree at that current iteration, we can simply check this value set because it would hold all the nodes values of the current recovered tree, right? And of course, once we actually initialize this set, now we actually have to get, I'm actually going to do this using a separate method. You probably can solve this problem without using an extra method, but I'm going to actually use a different method. I'm going to just call it recover, right? So I'm going to, again, call the recover method using that self keyword, so self.recover, and I'm going to pass in the root value, and I'm going to pass in an initial value of 0, right? We're using this helper function that I'm going to define right above, or right below here. Basically, we're using this helper function recover to actually reconstruct that tree by first passing the root node. That's the root value or root node as such of the current recovered tree. And we're setting its initial value or its current value to be 0. Right? That's the value that we actually start and build off from for future left and right child nodes that we build off in the tree. Right? We're calling this helper function within this initializing object or this initializing method. Right? And now we actually have to define and implement that recover function below, because of course we want our recover function to actually be defined in our class here, right? So I'm literally just going to call it recover, because really I don't have any other option because I'm calling the self.recover method above on line 11. So I'm going to call it recover, and it's going to take in 2 parameters, right? What are the 2 parameters? Well, of course, excluding self, it's going to be a node, and it's going to be its corresponding value in the current iteration, right? Self is basically to actually be able to use the self keyword while actually calling that recover method, right? That's why we need self as one of the parameters as such, if you will, for object-oriented programming for methods like this in classes, right? Basically, it's actually responsible, this method, for actually assigning the correct values to each corresponding node in the tree as we actually build up or construct our reconstructed tree, right? Or our non-contaminated tree. I think they don't really give us a definition or a vocab term for that, right? So this is a recover method that we're calling within our initializing object, right? So what is the first kind of conditional or base case we can have in this recover method? Well, if not node, meaning the node is null, we immediately simply return, because that means the node is none, there is nothing to process or to even parse, so we simply return. We don't have to do any operations or do anything in this current call of the function. But however, if we haven't returned just yet in this function, we're still going on, that means we do have a non-null valid node, and we want to actually update the node's value. So I'm going to set node.val, or the value of the current node, to now be the value that we have as a parameter, right? We're actually updating the node's value with the current value parameter that's being passed into the function, right? Just like how we saw, we're initializing 0 to the root node, because we're always guaranteed that the root node is going to be equal to 0. More to elaborate, the root node's value is always going to be equal to 0. And this is where that kind of recursion part of calling that method comes into play to actually build recursively our tree. You can think of this as like the DFS or BFS portion of actually recursively constructing the tree, building the left and right child nodes of each node iteration or call by call, right? So once I actually get the node value, I want to add it to my self.values hash set. So self.values.add, basically I'm adding to the current values or self.values hash set the new node value, right? Because of course this is another new node that we're actually adding on to the new or high level reconstructed tree, right? We're simply storing this new value in our set to allow those quick lookups, right? And now once we actually get this current node in our reconstructed tree in our value set, now let's actually begin the recursion. So in this recover function, I'm going to call self.recover, right? And for my parameters, I'm going to pass in node.left, basically going to the left node and applying the formula. And what was the formula for the left node of any node? That would be 2 times x plus 1. And so we're going to do 2 times value plus 1, because value is that x, value is equal to x, right? Value is basically the current node value of the current node. So 2 times the value, and like the formula says, plus 1. That's going to give us the formula, or that's going to give us the integer node value of the left node of the current node. And very similarly, we're going to apply recursion again to build the right child, or the right node. So node.right. And in this case, it's going to be 2 times value plus 2. Why is it plus 2? Well, because that's exactly what the formula says. The left nodes would have this formula, and the right node's value would have this formula for every single node in the tree, in the recovered tree, that is, right? We're basically recursively calling that recover method with the left child and assigning its value to be this formula, and recursively calling the recover method with the right child to assign its value as 2 times value plus 2. This is the BFS kind of portion or logic of this solution. This is to actually fully construct the binary tree, right? And we're doing this in the initializing object to initialize the object with this fully constructed recovered tree. And finally, now we have to work on our find method, and this is actually very straightforward, right? Why is it very straightforward? Well, because we actually made our lives a lot easier with this values hash set by actually adding all the nodes of our recovered binary tree when we actually built it in the recover method to our set. So once we actually recover the binary tree and append all those recovered or reconstructed nodes in the hash set in the initializing object, we simply have to return if the current target, so if the current target is in the values hash set, or in this case, the self.values hash set. And very self-explanatorily, basically, we're checking if the target is in our set. And it's going to be an operation that runs in big O of 1 or constant time, because it is a hash set lookup. And something important to note in runtime complexity, hash maps and hash sets always have a constant time or big O of 1 lookup and insertion time. Very good and important to know for algorithmic and data structure type interviews, right? So once we've actually, again, constructed fully the, or recovered the full binary tree from all negative ones from our input to be the new constructed tree, applying the values recursively for all the left and right nodes for each node using the formula as given in the problem statement, and initializing that constructed tree in our object when we actually get the object of the class, we're simply returning for every single find call if that target parameter node, if it's actually in the self.values class, which holds all of the node values of the entire reconstructed tree. And we're returning if the current node, or if the current parameter of the current call of the find method's target node is actually in that self.values hash set, which is going to be a big O of 1 complexity. So if I were to submit this, this would actually be an accepted solution. And as you can see, this really is just about as efficient as you can get it to be. So how does the code actually work as a whole? To really reiterate on a high-level rundown, basically, the init function, or the initializing function of this class, basically initializes an empty set of our object and actually calls a recursive method recursively to actually reconstruct that tree. And then this recursive helper recover function that assigns the correct values based on the given transformation rules or the given transformation formulas and stores them in that hash set, right, to actually help build that tree with the fully reconstructed or recovered values. And this find function simply just checks, well, if a current value parameter, if it actually exists in the set. And this hash set makes the search operation a lot more efficient, big O of 1 to be more specific. And that brings us to the runtime and memory complexity. So what is the runtime complexity? Well, for the recover function solely, for this recover recursive or helper function that we made, well, we'd visit each node once to actually recover it. And for each of those nodes, we would perform big O of 1 or constant time operations like the value assignment and the set insertion like we talked about before. And so the total time complexity would be big O of n, right? N would simply be the number of nodes or the number of operations that we make in the tree, the number of nodes in the tree, that is. And the find function, in terms of that runtime complexity, since we are actually using a hash set and we're also checking for existence, that would be big O of 1 on average. Again, it's really simple. Constant time operations for hash sets and hash maps, and so overall it's going to be big O of n for the runtime complexity. And for the memory or space complexity, we are actually storing all the unique node values in a set. That would be big O of n space. It's not a constant time space solution. This self.values hash set is going to actually grow linearly with our input size, basically the number of nodes in the tree, because we're storing all the nodes in the tree in our hash set. And so this is going to be a linear or big O of n runtime, or sorry, memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.